Hey gang, it's me. Welcome back for your nightly physics joy here. This little video here is about learning how to do projectile motion, or specifically projectiles launched at an angle. So now we're not just going to launch them horizontally off of something, but we're actually going to do kind of a more realistic flight path. You're actually launching it up at some sort of an angle typically, and to see what happens with that. So with these, hopefully you watched the other video and you're pretty confident with the other one. If you're fairly confident with projectiles launched horizontally, then these ones really just have an extra step, maybe, well, extra two kind of steps. But they're not that much harder. The hardest thing for students is to kind of keep an eye on all of the different little parts that are in there. So I'll try to point those out as we get to it. So with this, again, the couple basic things about projectile motion. Pardon me. Oop, hi, cat. It's my orange cat, and she's going to be a constant companion here when I do this. So keep in mind that horizontal motion, just like with the other style of projectile motion, horizontal motion is governed by inertia. So there's no acceleration. We can use the basic equations of when we're talking about horizontal stuff, that we can do the velocity is distance divided by time. So when we're talking about the x, we can just use our basic equation to it. The thing that makes these problems different now is that because when we're launching it, it's not truly horizontal. Our VI that we have is not all horizontal. As it was in the last ones, every VI we had was all VIX. But in this case, when we're talking about launching these things at some sort of an angle, then if I'm launching it straight up in the air like this, I've only got a little bit of X component and a lot of Y component. So you can kind of see where we're going to this. As we start to do these sorts of problems, you can't just assume that your VI is all X or all Y. Our vertical motion is the same as we've done before. It's all the same kinematics thing. We still have our acceleration due to gravity, so that's 9.81. And in this case now, this is where it gets really important, as if it wasn't before, to make sure that you're assigning positive and negative signs to it. So make sure when you talk about your acceleration due to gravity, it's downwards negative 9.81, because especially since a lot of your VIs are positive going in the other direction. And then the other big thing to keep in mind is that our VIY is no longer zero. We're not dropping it, we're launching it up into the air. So oftentimes in these, our VI is going to be positive, one of those components of that initial launch. Again, not just dropping it, now we're launching it upwards, so we have positive VI and a negative acceleration. All right, moving on. What else do we got next here? Let's see if I can get this going here. So our key step when we're doing these things is to use that concept of components, that when we were doing something horizontally, our VI was all in one direction. But now when we've got this sort of situation, our VI is at an angle. Hi, cat. Orange cat. So when we're doing this, that means that we have to turn this into our two different components, that we have VIX, which is what's going to be sending it horizontally and determining range. And then we're going to have VIY, which is going to help determine its altitude and how far up in the air that it's going. So again, these two things are really critical components to figure out. Keep in mind that your VIY is going to be positive and your VIX is typically positive too, because you're launching it downrange. Biggest mistake that students make, and I've kind of got it over here, this is that note to self. A lot of times students forget that there's the initial velocity, which is the velocity at an angle. Then you also have the components, the horizontal and vertical components, and these are different things. So the biggest mistake that students make when they're doing these sorts of problems is that they don't literally keep their X's and Y's straight, that they kind of combine the two different sections of it. So it's really important for you to make sure that as you're doing your work, you're thinking to yourself constantly, is this horizontal or is this vertical? Horizontal or vertical? And try to go back and forth with that as much as you can to try to keep those two components straight. So a couple of the key landmarks that we're going to use, similar to what we did in the other projectile motion. There's some things that you know about projectile motion in general anyway. And here, one of the things I like about this little diagram is it kind of shows you the comparisons about Vx and Vy as something kind of travels through its motion. So when we have an initial velocity, and here's our Vi, oops, sorry, get my pen back here. When we have our initial Vi, like this down here, our Vi here is this little blue arrow. And you can see that there's both a vertical component, the Vy, and the Vx, the horizontal component. And is that as you're going up, the vertical component gets smaller every single time. And that's because acceleration is the opposite direction. Vi is positive, or Viy is positive, but A is negative, downwards. So it gets smaller at every time interval. And then at the top, just like we're used to, Viy is equal to 0, or I should say not Vi at this point, but Vy at that point is 0. So I guess that would be like a Vf. if you're talking about that. And then as we go back downwards, now you're accelerating downwards and your VIs get larger for every second, or your VYs get larger for every second. If you take a look at the horizontal motion, the horizontal components, the VXs, are the same every single time. It doesn't matter at what point in this object's motion, the VX is consistent all the way throughout. So again, we got to be a little bit careful with keeping track of your X's and Y's. So with this, again, make sure that you're aware that the VI that's given to you has both horizontal and vertical components. So VI and VIX are not exactly the same anymore. You've got to use components thinking. VX, once you figure it out, is constant. It's going to be the same all the way throughout its motion. And again, we're doing our spherical chicken assumption of there being no air resistance. When we're starting to talk about the Y components, this is much more complicated. Our VIY is typically going to be positive in the upwards direction. Our AY, our acceleration, is going to be negative. And again, this is negative due to gravity. At the top of its particular flight, the VFY at the top, maximum altitude, would be equal to 0 for just an instant. And then the last little kind of trick that we can use, depending on what we're trying to do, is to keep in mind that VFY, this one down here, its final velocity is equal and opposite to its initial velocity if it's landing on the ground at the same altitude. So not launching it off a cliff and then having it fall even further or something like that. So again, with this one, VF on the ground is equal and opposite to VI on the ground, as long as they're both starting at the same altitude. Key thing here again is to make sure that you're really, really cautious about your positive and negative signs. Otherwise, you're going to get some really squirrely answers. But you're not going to know they're squirrely because mathematically your calculator couldn't care less. So be super intentional about whether you're talking about horizontal or vertical, and whether you're talking about upwards or downwards, positive or negative. So we're going to work our way through one of these example problems, and this will lead you through the 3 types of things that you usually get asked on these sorts of things. And then I'll have example number 2, and that's all I've got in this particular one. So example 1's got 3 parts to it. Example 2's just got 1 part to it. I'll leave example 2. I'll kind of tell you to pause it and have you kind of figure it out, and then we'll recheck how we're doing on this one. So this is a typical kind of a rocket launch problem that we've got, where they give you a picture where you're launching this rocket at some sort of an angle. So we've got, I should do that. That's not right. I should draw, hold on, let me erase that little guy. I should draw my VI is, let's see, like this, 5 meters per second is my VI, and then it's at something like 53 degrees. And my picture is a little bit shy, but we'll count it good enough. 53 degrees. When they say above horizontal, that's all they're talking about is the kind of the regular upwards kind of direction. So there's our VI. By the way, when you see the answers to this one, 12.5 meters per second is the total made up number. It's really not very fast. So our numbers are going to seem like, wow, that didn't go very high. That's okay. So question number 1, how long is the rocket in the air? So how long, when we're trying to do this one, we're going to be finding time. And again, just like our other projectile motion problems, time is going to be that key between navigating between the X and the Y components to it. So how long is the rocket in the air? Question B here, how far away does it land? That's going to be dx. We're looking for range in this particular one. And then for this one, the rocket's maximum altitude, this is going to be dy. We're looking for height in this one. So these are the 3 things that we're going to kind of try to solve for on here. So first thing that we need to do in our problem solving approach, I'm going to move that up a bit, is we have to use our components. We have to figure out VIX and VIY are. So with these, oops, that's supposed to be a Y. Hold on. Really not very good at this writing in one place. I'm thinking about something else. VIY, there we go. So with these, again, we're going to be taking a look at sine and cosine to figure out what those components are. This is our adjacent side, so this is going to be cosine. This vertical side here is going to be our opposite side, so that's going to be our sine. So with this, if we're trying to find our VIX, we're going to do the cosine of 53 degrees times 12.5. And if we're going to do VIY, it's going to be the sine of 53 degrees times 12.5. And when I did these calculations, I can figure out what these are. Cosine of 53 times 12.5. Oops, if I did that right, that would help. 12.5. I know that VIX, so VIX is going to be equal to 7.52 meters per second. And then VIY is going to be the sine of 53 times 12.5, which is VIY equal to 9.98 meters per second. I know that both of these are going to end up being positive because it's moving horizontally across the ground, and then this is going to be VIY because it's being launched up in the air. So again, I'm giving these both number signs to try to be able to figure what they are. All right, so how long is the rocket in the air? Well, how are we going to figure this out? We can figure this out using either horizontal or vertical motion. And for this one, in terms of trying to figure out what time is, we can kind of go either direction. For me, I typically do this using vertical motion because I know a couple things about its vertical motion. So if I'm talking about VIY, I now know what that is, 9.98 meters per second. And again, that's positive. I can talk about going up to the air or back down to the ground. So I'm going to talk about just going up to the top of the flight because that's what a lot of students tend to do. So I would do VFY would be equal to 0. This is at the top. So it is at maximum altitude. Acceleration is going to be equal to negative 9.81 meters per second squared because, again, it's going upwards, but it's falling downwards. And so then I'm trying to find time. So do I have an equation that links all of these three things together? Of course I do. VF equals VI plus A delta T. And I can plug my numbers in. 0 equals 9.98 plus negative 9.81 times time. So negative 9.98 equals negative 9.81 delta T, and delta T is just under a second. 9.98 divided by 9.81. I get 1.02 seconds roughly with 3 sig figs, 1.02 seconds. I know I've mentioned this before, but if you ever get negative time, like you forgot to put the negative sign here, if you get negative time, that means you just went back in time. That's not okay. That means you dropped a negative sign somewhere, and mathematically it may not change it, but it might. But that's kind of a note to self that you need to kind of double check what it is that you're doing, and maybe take a look at what you missed. So we know that how long it's in the rocket, how long it's in the air. Okay, well, this 1.02 seconds, where is that? 1.02 seconds is to the top. That does not tell me how long the rocket is in the air. This means I have to do it times 2 to get the full time for it to be in the air, which is 2.04 seconds total. So it's 2.04 seconds in the air until it goes up, gets to the top at 1.02 seconds, and then comes down in 2.04 seconds. We're going to assume that it's symmetrical flight. Again, I know that's a bit of a spherical chicken assumption, but that's okay for what we're doing here. All right, question number 2. What else can we do here? Question number 2, how far away does it land? All right, well, if we're trying to find range, now we're not dealing with the y components, now we're dealing with the x components. So, and again, I've written this before, if we're talking about range, range is dx. And whenever I'm talking about dx, remember, there's one and only one equation that we use for this. Velocity is distance divided by time. The x component is governed only by constant velocity, so it's the easiest of all of our equations to use. So how do we fill this in? Well, you fill in your Vx. Here's the number one mistake that students make. You do not use Vi. Students want to put 12.5 in here because that was the initial velocity, but that's not the horizontal component. And that's really, really important to keep track of in here. Go look back over at our work over on the right. The total velocity of it, VI, was 12.5, but horizontally, because it was at such a steep angle, really only 7.52 meters per second of that initial velocity is contributing to its horizontal motion. So again, this is the number one key mistake that students make. You have to use Vx here. So this should be 7.52 meters per second equals distance, our range, over time. And again, our time here, because we're talking about up and then down, we're going to use our full time, 2.04 seconds. Hi, Kat. Would you not help? Thank you. Move. Thank you, Kat. So again, 2.04 seconds. By the time we do the math on this, it becomes out to be 7.52 times 2.04 equals dx. And in this case, what is it? 7.52 times 2.04 gives us a value of, well, with sig figs, 15.3 meters equals dx. Like I said, not exactly a very exciting rocket. 15 meters isn't all that far. It's like 15 yards. Like, oh well, whatever. 15.3 meters is going to be our horizontal component of our displacement. That's as far as it went. Pretty lame, I know, but close enough. Just checking my other work earlier to make sure I'm doing this right. All right, what's our last question? Then we're done with that part. Last question now is, what's the rocket's maximum altitude? So maximum altitude is about dy again. We're back in this vertical component again. So for maximum altitude, This is the one where I'm talking about just going up to the very top. I don't care about how long it takes to get back down. So I know what my VIY is here. And the question is what I use for my VFY. And this is where I can use that case where VFY equals 0 at the top, at the maximum altitude. Again, I'm not talking about all the way to the ground. So you got to maybe think about what that VFY is. My VIY is 9.98 meters per second. Again, it's going upwards. And then I know my acceleration is negative 9.81 meters per second squared. Again, negative sign here is going to be really critical. And now I do know what time is for this in order to figure this part out. Because if I'm trying to find maximum altitude, I'm trying to find dy, and I think most of those equations have time in them. They don't necessarily have to. I could use this one, vf squared equals vi squared plus 2a delta d. That one works. I can also use the df equals di plus vi delta t plus 1/2 a t squared. I can use either one of these equations and it should give us the same answer both ways. So again, with this one, I can use 0 squared equals vi. Again, it's really important. Make sure you don't use the total vi. You're using VIY, the vertical part of its motion. So I've got 9.98 meters per second squared plus 2 times negative 9.81 times delta d. And again, the negative sign here is really critical to make sure that you've got that part working out. 9.98 times 9 point, what is it? I need to do squared. What am I doing here? All right, 9.98 squared. So this 0 equals 99.6 minus 9.81 times 2 minus 19.62 times delta d. This is 19.600. Negative 99.6 equals negative 19.6. And again, this is where the negatives should work out. D is 99.6 divided by 19.6. 99.6 divided by 19.6, well, 2. And I get a time or distance of 5.08. Yeah, meters. Yeah, it only went up 5 meters. Man, this is a lame rocket. Sig figs, this would be 5. Is that right? How many sig figs do we have in here? 3? Yeah, 5.08 meters. This is positive. If you didn't do this negative sign in here, you'd actually get a negative 5.08 meters, which would mean it went down into the ground 5 meters. I'm not quite sure how that would work. But again, you want to make sure that you've got that. Double check to make sure you're always doing your positive and negative signs. So again, the math and stuff is all exactly the same. We're using the same kinematics equations. We're using the same horizontal and vertical components. That horizontal is constant velocity, that vertical is acceleration due to gravity. The only thing that really makes these different is that now when we're talking about VI, we have to take that initial first step of resolving VI into components, X and Y components. And then we have to be really, really, really careful about making sure that when we're doing our math in our later steps that we're using the VIY or the VIX, that we're not really using VI at all. Okay, so let's time for you to take one up here. So here's example number 2. It's a football problem. I'm going to encourage you guys to hit pause and see if you can kind of figure this one out. Take a moment and, like I said, hit pause, work your way through it, and see how far you get with it. Obviously, I'm not really going to pause because I'm recording this, but you should hit pause, and I'll be back in just a second and start working this one out. All right, did you hit pause? Are you back? Okay, so in this case, we're launching a football. So we got a football. It's being launched at 38 degrees. I should draw that as a straight line. Wow, nice Bedwell. Let's try that one more time here. So we're launching it at, in this case, about 38 degrees. So there's our 38. And it's got an initial velocity of 20 meters per second. And again, that's VI. That's not VIX. I don't know why that one like that. VI meters per second. There we go. And we're trying to figure out where will the ball land. So if you think about what this is looking for, this thing, when we're talking about this is called range. I want to know how far downhill or downfield I'm kicking it, which means I'm trying to find dx. I'm trying to find that. I don't care in this particular problem how high the altitude is or how long it's going to be in the air. I'm just asking for this part. How far downfield is it going to land? So typically, if I'm asking you dx, that means you're going to have to find something about dy first or whatever to figure out what your time is. If we're doing this one, we know this. We're going to need Vx equals dx over t. That's the only equation that we have. We'll know what Vx is because we'll be able to figure it out from our initial stuff. We'll need to find time in order to make this equation work for us. So how do we do that? All right, components. Cosine of 38. Cosine is the adjacent side. So cosine of 38 times 20 is going to be giving us our adjacent side here is VIX. And the value of that, cosine of 38 times 20, gives us an initial horizontal velocity of basically 16. It's 15.7, 15.8 meters per second. I'll leave it with the one extra sig fig. We only have 2 sig figs in our problem. I'll leave it with the extra one as we're doing our calculations. That means that sine of 38, sine is going to be the opposite side. So that's going to be our vertical component, VIY, and that is going to be the sine of 38 times 20, 20 equals 12.3 meters per second. Okay, both of these are positive because I'm kicking it up and I'm kicking it downfield. I also know acceleration is going to be negative 9.81 meters per second. I don't know what time is yet, but I can figure some of that out. So how do I want to solve this one? Well, we need to figure out something with time and what we're trying to figure out. So we can usually go back to my favorite one, which is this one, VF equals VI plus A delta T. I don't know why I always go back to that one. Maybe because it's a simpler equation. I don't know. And we can plug our values into this one and figure out what T is. So what do we have for this? Well, if we're going to do this kind of thing, usually we do it with our VF is the maximum, at the maximum point. We would say that our VF at the top of the hill would be 0. And our VIY, and again, this has to be VI since this is the Y component that we're dealing with right now. Our VIY would be 12.3 plus acceleration, negative 9.81. And this would be delta T. Now this delta T is only going to be the time to the top. It's not going to be the full time. So I'm going to have to double this when I'm done. So negative 12.3 equals negative 9.81 delta T. That means that delta T is equal to 12.3 divided by 9.81 is equal to 1.2, looks like 25, looks like what the value is. Yeah, with sig figs seconds would be our time. This is 2 top. And again, this is the key, one of the key things that students remember or forget to do. So if I want to know the full time, like I'm going to use over here, I have to do times 2 to get the full range. So 1.25, well, I know what the answer is, times 2 is going to be, equals 2.50 seconds to ground. And again, that's one of the things that students forget to do. So now I can use my other equation over here, which is Vx equals dx over t. For Vx now, make sure that you're using Vx, not the initial complete velocity. You're not using 20 here. You're using the horizontal component, which is 15.8 meters per second, equals dx over the time to ground, 2.50 seconds. Again, make sure that you double that. Otherwise, you're not getting nearly enough distance. 15.8 times 2.50 gives me a dx of 39.5 meters. If I round that to 2 sig figs, it's 40 meters equals dx. So where's it going to land? Basically on the 40-meter line or the 40-yard line, I guess if you want to call it that. So that is your final velocity for dealing with that. So there you go. Dealing with projectiles launched at an angle isn't super tricky. If there's homework problems that have you launch it, up where it lands at a different height than it launched at, they're still done exactly the same way. Your dx may end up being negative if it's falling below. Your dy could end up being negative if it's falling below the launch height. There can be some other kind of weird little things that happen, but the process is exactly the same. So your key takeaways today. Again, it's still projectile motion. Horizontal is constant velocity. Velocity is distance divided by time. Vertical is governed by acceleration and our kinematics equations. You need to make sure that you resolve your initial velocity into its x and y components. That's a critical step. And then make sure that you're using the correct component when you're using your equations later on. So if you're using horizontally, velocity is distance divided by time, make sure you're using Vx, not the initial velocity, just the Vx, the x component. And if you're doing any of the kinematics equations, you're using Vy. Again, just the part of its initial launch that got it up in the air. So there you go. I hope that helps and hope you're working through your homework pretty good. I'll be setting up a Zoom meeting so we can work through some homework here pretty soon. And hopefully I'll see you soon, right? Spread kindness, not corona. And I'll see you guys in in the next video. Have a good one, you guys. Bye.